Hello, and welcome to the WSTS virtual tutorial on synchronized clocks. My name is Greg Armstrong, and I'm a Principal System Architect at Renesas Electronics. Some of the topics we're going to cover today on synchronized clocks is looking at time, phase, and frequency, and how they can be distributed over a network using phase lock loops, or PLLs. We'll look at the basic principles making up a PLL, and also how does a PLL respond to different noises that may be injected in the network. We'll look at different operating modes a PLL can provide, and then look at interesting applications such as clock combining. In the other tutorials, you've been introduced to concepts of frequency, phase, and time. And we all know what time is, with a unit of seconds. Phase is the angular of a rotating vector. In clock terms, it can be looked at as the period of a repetitive signal. Frequency is a statistical term, normally representing the number of events that happen per second, with a unit of hertz. Jitter, wander, and phase noise, which you'll hear more about in other tutorials, is a variation of the clock's frequency period or phase, and it essentially is a phase modulation of a carrier clock. In the other tutorials, you've already been introduced in concepts like synchronization, or not being synchronized, or even synchronized. But what do those really mean? Well, this slide tries to represent that graphically by looking at a counter that might be clocked by different sources or the same source. At the top of the slide, you can see two different frequency sources providing a clock to a counter. Now, although they might be running at the same what we call nominal frequency at 125 megahertz, there's always some sort of error that is introduced by the frequency source, typically measured in parts per million. So two different frequency sources may have two different part per million representations. Looking at this on a count over time graph, you would not see any relationship between the two clocks. They might have a similar slope, but the slope may be drifting from one another, and they are not definitely aligned in terms of having a similar concept of time. With the use of a phase lock loop, we can use a same frequency source to source the clocks for both counters. Now we can have a clock that is at the same nominal frequency and the same parts per million offset. This is what we call frequency synchronized, or sometimes referred to as synchronized. If you look at the counters in this case, here over a count over time, they would have exactly the same slope because they are frequency and phase synchronous. However, those counters could have started incrementing at different points in time. So if you look at the time relationship, there would be some offset between them. So how could we get phase and time synchronization? Well, this could be done by using some mechanism to control when the counters start incrementing and give them a common time base or some time source base to allow them to start their time at a same point. An example of this could be like a 1 pulse per second that could be used to clear a nanosecond counter. In this case, when you look at the count over time, you now see them all aligned, following the same slope, and also have the same time label associated with them. So I've already mentioned phase lock loops a couple times in this tutorial, but we really haven't talked about what are they. So let's look at some of the principles of a phase lock loop and some of the key components that make up the system. So what does a phase lock loop do? Well, as the name implies, a phase lock loop tries to have an output phase relationship of a clock to be the same as the phase of an input signal. It does this by bringing the output signal back to the input as a comparison, and it's normally called a feedback loop. This allows a phase lock loop to generate a clock that is both phase and frequency locked to the input. And the output clock can be the same frequency, or using some sort of integer or fractional divider on the feedback, you could actually make it an integer or fractional multiple of the input clock frequency itself. Doing this, you will find some sort of edge-to-edge phase relationship achieved at that common ratio. Let's now look at some of the building blocks that make up a phase lock loop, starting with the phase comparator. The phase comparator measures the phase difference between the input reference and the feedback, which is coming from the output. Most digital phase lock loops implement this using a time-to-digital converter, or TDC, which timestamps the rising edge of the reference input and the rising edge of the feedback, and takes the difference of that as a digital phase error word and outputs it to a loop filter. The TDC must be able to timestamp both edges and maintain the phase error that might go beyond one period of the reference input. And this is due to jitter and wander tolerance requirements that may need to be established by the phase lock loop. For example, the widest one known in telecom is 18 microseconds peak to peak. The phase error is then passed along to the loop filter block. The loop filter is a low-pass filter that filters out high-frequency noise on the clock, or jitter, and allows low-frequency noise to pass through, or wander. The loop filter is a combination of a proportional term and an integral term. We won't get into the mathematics of that transfer function, but you can look at it as the proportional representing the phase traceability of the input reference and the integral representing the frequency. The integrator makes up an additional pole within the filter, and you sometimes see the filter referred to as a second order filter. And the PLL with that implemented will be referred to as a type 2 PLL. The loop filter determines the bandwidth of the PLL, or the cutoff frequency. But other functionality may be contained in the loop filter, such as phase slope limiting, which limits the rate of phase change when you're tracking a clock. There could be lock ranging to determine what range of phase offset will you track a clock, or holdover functionality when you lose the input reference. The step response will have an overshoot, which is what the integrator is meant to use to try to dampen that effect, which will try to limit what we call gain peaking or noise peaking onto the clock near the cutoff frequency. Finally, the control signal from the loop filter is used to control a voltage control oscillator, or VCO. The VCO is sped up or slowed down based on the signal coming from the loop filter. With digital implementations of a phase lock loop, the VCO is replaced by a digitally controlled oscillator, which uses a frequency puller to speed up or slow down a free-running oscillator. This oscillator can be a crystal oscillator, or a MEMS oscillator, or any form of oscillation of a clock. Because it's digitally controlled, the control signal coming from the loop filter is generally represented as a frequency control word. The output of the DCO or VCO is then fed back to the phase comparator to close the loop. So a question you may ask is, are phase lock loops important for packet-based clocks? Well, the short answer is yes. You can look at it as a timing protocol such as 1588 as really just a phase or time comparator, which only makes the front part of a phase lock loop. In order to synthesize a clock that is synchronous to your grandmaster clock, you still need to follow the fundamentals of some sort of low-pass filter and some sort of VCO or DCO to synthesize the clock. And again, you have some sort of feedback mechanism, such as the local timescale timestamper that timestamps the arrival and departure times of the packets to the local clock. Now you may ask, well, yes, but I heard trying to recover a clock over a network that does not fully support 1588 is very difficult. What are adaptive filters or filtering techniques? Well, adaptive filter represents what may occur prior to the low-pass filter, where you might actually do some packet selection based on the noise of the packet experiences as it goes through the network. Because you are doing packet selection, much less packet or phase information might be passed along to the loop filter. So the loop filter may operate at a very low bandwidth, much lower than might be used for physical-based clocks. Because of this, you may require a more stable clock source to allow the recovery of the clock, like an OCXO or oven-controlled crystal oscillator. Or you might have to use some physical layer assistance, such as Sync-E, to help stabilize the clock during the filtering process. Now that we looked at the different components that make up a phase lock loop, we can look at the different responses the output has in relationship to the input. And there's really kind of two responses you can look at. One is the phase relationship of the output to the input as it's tracking the clock and locked. And you can also look at the relationship as noise is introduced at the input. Is there any sort of gain peaking that is occurring near the cutoff frequency as you attenuate the high frequency noises. So again, this is typically looking at the wander or pass band of the noise being allowed to pass through and limiting the gain peaking of that by damping the effect and filtering the high frequency noise so that it is cleaned up so you have a nice clean clock that can be used to source SerDes or high frequency physical layer devices. So let's now look at the impact phase lock loops have on the response to that injected noise. We won't go into a lot of details because there's other tutorials that will cover this, but it'll at least give you an idea of the concept of low pass filtering and high pass filtering, and even other concepts such as band pass filtering. I've already used terms of jitter and wander throughout the tutorial, but what is jitter and wander? Well, jitter and wander are noise or other disturbances that happen on the clock when you compare it to an ideal reference. Short-term variations or high-frequency noise is referred to as jitter, and long-term variations or low-frequency noise is referred to as wander. The ITU-T G.810 actually defines noise frequencies less than 10 Hz as wander and frequencies greater than or equal to 10 Hz as jitter. So if we look at jitter and wander, what is the function of a phase lock loop? Well, a phase lock loop is supposed to attenuate jitter or filter jitter, but allow the transfer of wander. In other words, you want to tolerate the noise at the input without losing lock to the reference. So very high frequency variations, like they're shown here in red, are filtered out to get a clock that represents in blue that is tracking the input reference. So what is the response of a phase lock loop to injected noise? Well, there's really two noise sources in regards to a phase lock loop. One is coming from the input reference itself. So typically here, we are filtering out the high frequency noise that are coming in from the input reference, but tracking the low frequency noise. So you generate what we call a low pass filter response, where everything below the cutoff frequency or the bandwidth of the PLL is passed through and everything higher than that cutoff frequency is filtered out. Well, in order to filter out the clock, you have to still resynthesize that clock and represent those high frequencies in terms of phase noise. So a lot of times the noise that is coming at the high pass comes from the local oscillator or the local clock. In this case, everything from the clock that is lower than the cutoff frequency is filtered from the oscillator, but anything above that passes through. So what that means is if there's any sort of noise on the local oscillator, such as maybe temperature variations that impact the clock, those are going to have a direct impact to the output. But any low frequency noises of the clock, such as drift or short-term variations, will actually be filtered because you're tracking the input reference. As I mentioned earlier with the loop filter, a phase lock loop can be looked at having different modes of operation as it's trying to acquire and track a reference input clock. The PLL really has three modes of operation. Free run mode, which is kind of as the name implies, is when the DPLL has no input to track, so generally at startup or initial power up. In this case, the output clock is just running at the nominal frequency of the local oscillator. You can look at it in the diagram below as if the switch is actually open between the loop filter and the memory. In normal or lock mode, the DPLL is now tracking an input reference. And we use the term lock to generally represent that the output clock is both phase and frequency locked to the input clock. And you can look at this as switch 1 is now closed. Well, what if the input clock fails while you already had information while locked to that input? Well, here we can use a memory technique where we can store an average change of the different frequencies that are being sent to the VCO. We can store that information and use that to establish a long-term frequency of the VCO on the loss of the input. And we call this holdover, where we're holding the last frequency information on the clock until the input is restored. In this case, you can look at the switch as being in position 2. And now the clock becomes an autonomous synchronous source because it's now has history of the traceability to that input reference. But the short-term and now long-term variations are now coming from the local oscillator. Looking at holdover at both the frequency and time domain, you can see that with frequency, there's going to be a known drift of the clock while it's in holdover. Generally, there's two components that make up this drift. One is the initial frequency offset, which is an offset that the PLL will initially establish after it enters holdover. And then there's the drift, which is tied to the oscillator in terms of how the clock drifts over time, or the long-term variations of the crystal oscillator. Looking at from the time domain and looking at what we call a time error, you can see that it has a much different response. Whereas the frequency response is a little bit linear in the way it's represented, when you look at it from a time relationship, you actually get exponential acceleration of the time error, which is why different oscillators have different capabilities to try to hold phase or time over long periods of time. Now that we talked about a lot of the general concepts and principles of a phase lock loop and also the different characteristics of noise transfer, let's look at some interesting applications that can be used with phase lock loops, such as clock combining. So what is clock combining? Well, clock combining can be looked at if we look at two phase lock loops independently. They're each going to have their own characteristics of a low pass filtering and a high pass filtering characteristics, which the low pass represents the input to output relationship and the high pass represents the local clock to output relationship. Well, what if we had two PLLs running at different bandwidths or different cutoff frequencies? Well, in this case, what if we took the output of one phase lock loop and used it as the oscillator source of another phase lock loop? Well, by doing this, we can actually create what we call a band pass filter between the one clock and the other. And if you look at the injected noise, the noise that comes in from the one clock actually is filtered when you look at it from the noise coming in from a second clock. So you get a low pass filter of the red will pass through, but the green low pass filter is actually filtered out. So you only get an attenuated effect at the low frequencies. And then between the two cutoff frequencies, you get this band pass effect, where the noise in that band pass that's coming from this source is directly passed to the output of the other source. And then once you exceed the cutoff frequency of the second PLL, then the oscillator noise will then take effect as part of the high pass filter. If we look at the spectral densities, you can look at it as almost combining the different phase relationships of the outputs and what sort of noises can be passed along to the output clock. Generally, very high frequency noises are coming from the local oscillator, which are very clean in terms of having a very good phase noise floor relationship of the clock. When you start tying in the other effects of such as the sync E clock and a 1588 clock, you can create this phase noise effect where you only take advantage of the phase information from each clock, and you can take advantage of very good short-term traceability coming from something like a time source coming from UTC versus something that may be coming from a very good long-term frequency source such as synchronous Ethernet, and be able to synthesize nice, clean, high-frequency clocks using crystal-based techniques, which give nice, clean edges and very minimal high-frequency noises when you resynthesize that clock. So now you might be asking, well, that's neat, but where are the applications? Well, actually, there's already applications happening today, even with 5G deployment. One is with the enhanced primary reference time clock. Here, you can see the usage of both a GNSS receiver and a cesium clock to combine the benefits of each into one common clock synthesis, or the primary reference time clock. So you can take the benefits of the frequency coming from the cesium clock, which has a very good long-term frequency traceability, and that of a GNSS receiver, which has traceability to UTC, and combine it to get a primary reference time clock for the network. And he also used this technique today in telecom boundary clocks, where we combine the benefits of the physical layer synchronization, such as synchronous Ethernet, with that of the P2P time clock to stabilize the clock during the filtering of the P2P time packets, but also if there is a loss of the P2P packets, you can use it to establish a good long-term time holdover of that P2P node. In fact, if you look at the ITU-T recommendation for telecom boundary clock, you can actually see where they define the bandpass effect that happens when you use physical layer assistance with the P2P clock, or the bandpass effect. I hope you found this tutorial very beneficial, and if you have any questions, feel free to reach out to me at greg.armstrong.ew@renesas.com. Thank you.